so let's look at natural sciences part 2. Don't believe the results of experiments until they're confirmed by theory. Okay? We talked a little bit about this last time, the idea of the scientific method. We've been talking about it the last 2 times, actually. So let's kind of look at what sort of scholarly people say about this thing. Okay? So, according to the scientific view, that science is not so much a fixed body of knowledge, but a way of thinking. I would argue that science is a method. Science itself science isn't a book of knowledge. Science is a way to get through solving problems, okay? So how are each of these similar to science? Baking a cake using a recipe. Is that like science? Do you follow a method? Sure you do. Is there sort of an outcome at the end? Do you test that outcome? Okay? How about repairing a car? Is there a method for that? Is there a way to test that? How about speculating on the origins of the universe? Solving a murder as a detective? Solving a crossword puzzle? Is there a method? Is there a way to test it? Is there a hypothesis? So aren't all those things science as well? Again, it's that big question. What qualifies it as science and what doesn't? Maybe it is the case that if you follow a specific method, you're performing a scientific study. Science is a long history of learning how not to fool ourselves. Okay? Does anyone know the nickname of Richard Feynman? I'm sure Mr. Libby's talked about Richard Feynman. What's his nickname? The Great Explainer. Okay, so I talked about inductive and deductive. Inductivism is often used in the realm of science to kind of break down the scientific method. And the way it describes it is observation, hypothesis, experiment, law, theory. Now, this is not the sort of order that you guys presented it in when you did your scientific method. But here's the argument to be made to put it this way. You have to start with observation, and what that means is you observe something in the natural world. Like, oh, look, when I drop this phone, it hits the ground. That's the level of observation I'm talking about, that you experienced some event. You then form a hypothesis. So, for example, in our activity today, you observed this device that you didn't know what it was. Then you formed a hypothesis. Then you performed experiments. And then these last 2 words in the realm of science are often debated, right? Some people take the word theory and place it up here at spot 2 and make those 2 words equivalent. And in some places in the world, that's true, right? When you say, I have a theory about something, you're also saying you have a hypothesis. But to science, that's different. Think about the way the word theory is used in science classrooms, right? Things like, how is it used? Like, for example, I'm not going to put words in your mouth. Where have you heard the word theory in a science classroom? Or read it in a science book? The theory of what? Have you guys actually studied any science whatsoever? It seems like you guys do. Theory of relativity. There you go. Okay? Now, where do you hear the word law in a science classroom? Okay, but give me an example. Sine law? Well, that's more of a, okay. That's more of a math thing, but we'll go with that. Any other laws in science that you can hear of? Newton's law. There you go. Newton's law. Okay? So, just one second. Hi. I'm in the middle of a class. Okay, so Newton's law, for that example, the theories and stuff like that, so they do fit together. What scientists, and again, it's debatable, what scientists often say is that the laws form the theory, right? So you have laws that eventually form a big over-encompassing thing called the theory. Okay, so a good experiment at the experimental stage should have these features. And you guys know this if you've studied science, that you should be able to control your experiment. For example, only vary one little thing at a time. If you have too many uncontrollable variables, you don't have a very good experiment, okay? Measurability. The ability to put numbers and quantities on something. Again, we've talked about this. Repeatability. The fact that your experiment can happen over and over again and you don't have outliers in your experiments. Okay? If you're getting this from experimentation, then you can start to form the basis of deciding, you know what, this is now going to be a law. Okay? So that's kind of where science goes with that. If your results do not conform to your hypothesis, then you need to go back and start again. You throw it out, and obviously your hypothesis was wrong. But if you develop a law and then you start developing other laws and other experiments start confirming things, you might be able to develop what we called a over-encompassing theory to explain the laws. Okay? And that's what scientists generally, in the realm of the natural sciences, tend to use those words. Okay? They tend to have those sort of context or connotation to those words. Okay. So let's take a look at some of these scientific method things in terms of some specifics. So observation, a big part of this. So Kepler was able to develop his laws of planetary motion because actually it was another astronomer who made a lot of meticulous observations, and Kepler was able to use those and discovered anomalies within his observations. And it was Kepler who developed his sort of hypothesis based on other sort of data that came from another astronomer. Okay? Technology helps in the sciences, right? And by that I don't mean computers, but I just mean innovative new technological ideas help to drive science forward. For example, Galileo, who invented the telescope, obviously that invention, that piece of technology pushed scientific discovery quite a much forward. Imagination, we don't tend to think of that so much in science, but that's a big part of it. For example, there was a 3rd century BCE Greek astronomer who suggested that the Earth went around the sun. 3rd century BCE. But his ideas never really caught on, right? He was right, but nobody really kind of thought he was just being imaginative, okay? Obviously, and Tanner brought this up, mathematics and science tie together quite well, okay? It's hard to do science without doing some level of math, okay? And then another thing is that science is often not our first thought. Science is what my wife always describes as counterintuitive. Right now, you're spinning 1,000 miles an hour. You are traveling 1,000 miles an hour right now on the Earth as it spins at that speed. But we don't tend to think that way. Okay? It seems counterintuitive to think that that's what's occurring, but it is, right? So sometimes we have to break away from our intuitive thinking to kind of come up with better ways of thinking about science. Do you guys have to read Tolstoy in literature class at all? Okay, so we'll conclude today by sort of deconstructing that first level, the observation problem, okay? So if science is based on observation, right? So if I drop this remote and it falls and I observe that, before I go to the next level and make a hypothesis as to why that happened, let's analyze what's wrong with just me looking at or observing that event, okay? First of all, relevance. And we saw this last year when we looked at the senses, that we sometimes have no idea what's going on around us. We have to limit our own observation. For those of you who might remember the moonwalking bear from last year, we don't tend to always focus on certain events. We tend to we'd be overloaded if we do. We filter things that we observe, okay? We are selective in our perception. Okay, so for example, you're going to do an experiment last year in chemistry. You might feel that temperature is an important part of that experiment. But do you ever think about the number of people in the room? Because that actually affects the ambient temperature in here. I can attest to that personally, that if there was like 20 or 30 grade 9s in this room would be a lot hotter than it is right now, okay? 1 second, Ms. Peters, I'm almost done. Okay, the expectations, okay, a so-called self-fulfilling prophecy that you expect things from an experiment, okay? Expert knowledge, okay? Certainly someone who's looked through a microscope many times will be able to see things through that microscope differently than someone who's looking through it for the first time. Okay? So a lot of these go into affecting that level of observation. And we talked about this in previous units, the observer effect. Okay? The effect that an observer has on the environment that they're observing. Remember in the natural sciences, I proposed that you guys are all part of a CBC documentary on theory of knowledge, and that actually one of you isn't a high school student, but is actually implanted in here right now, posing as a high school student to observe that. Okay? Or for example, at a simple science experiment, when you stick a thermometer in a cup of tea to measure the tea, you're not measuring the tea. You're measuring the temperature of the tea with a thermometer in it. And that's a big difference. Okay, we're going to wrap up there, and Miss Peters just wants a minute of your time, because that was the end.